Assalamu alaikum. Welcome again. In this problem, we have 4 different balls, and we have series connection. We have also a parallel connection. Okay, so let's draw this problem in a 2D resistance schematic. So how do we do that? We start by a point at the left side. We have the Q flow comes from that point. Okay, we show that. And we have T1, which is known. Okay, so this is T1, and this is, we can say here you have T2, at this wall you have T3, and this is T4. Okay, so let's draw with respect to those temperatures. You have resistance A here, then you have temperature 2. Okay, temperature drop that you have between 1 and 2, that is because of the resistance coming here. Okay, so this we can analyze what happens here by just knowing the resistance, and T1 we can know T2. Okay, but also we need to find Q. We need to know what Q value is. Okay, so we cannot go straight forward and find T2 before we find this one. Okay, so we will take as overall balance. We will find between 1 and 4 the overall resistance and find Q. Then using that Q, we can also find the interpoints. Okay, so let's finish the diagram. Here you have resistance B being connected in parallel to resistance D. Okay, then you have a point after this parallel connection, which is T3. Then between T3 and T4 you have resistance C. After that you reach to T4. Okay, so you have the area of the cross section. So let's start putting the or let's rearrange this diagram again. We have Q, we have T1, we have only one R equivalent. Okay, equivalent resistance of all these, what we can say as overall heat transfer, like reverse of overall heat transfer coefficient. You have an equivalent resistance, then T4. So from this relation, first of all, just find the overall resistance. Then we can find Q from this diagram. Then we can go back again, since we know Q, so we can after that calculate the other temperature values. So first step, just after you draw all these, find RQ. How do we know RQ? It's the same job that we do when we have electrical resistance in series and parallel. So you take RA, okay, plus we need to find RBD. Okay, the equivalent of BD also you are adding, because that's equivalent of BD also is series, connected as series to RA. Okay, and RC. How do we know RBD? RBD is in parallel connection, so that will be 1 over RD plus 1 over RB in power minus 1. Okay, so that will correspond to RBD. Now we are very close to finding RQ. Let's put all resistance here. What is the resistance at wall A? Okay, so if you remember, resistance is proportional to length and proportional to okay, if L is bigger, you have more resistance, and inversely proportional to area and inversely proportional to K, because when you have more area, you will just allow to heat to pass through your wall. Okay, so you have more area, that will be easy for the heat to pass through your wall. So they have like reversely proportional to each other, and also here reversely proportional. But when you have long distance, you are making heat's job or heat flow's job more harder. So you have long distance, that means more resistance. High area, it can pass easily, so you are increasing the area, that will reduce the resistance, and also increasing the conductivity or thermal conductivity of the material also, that will reduce the resistance of, so they have inverse relation. So now let's say RA will be equal to from these relations, just LA, okay, L1 we can say, okay, this is L1, L2, L3. L1 over the other things that which is A, which is constant through this wall, AC, you can say. Then you have K here, KA, okay? And RBD is 1 over RD. Okay, what is RD? Let's find RD first, or RB first. It's L2, L is same, but cross-sectional area decreases to half. So you have AC over 2, or you can say 2L2. Instead of putting L over 2 here, you can, that will jump to the numerator, so you can put it like this. Then you have AC times the K, conductivity of B. Okay, just let's go quickly. You have the same idea here, same length, same area, and different conductivity. And you have RC is L3 over AC is same than KC. Okay, so let's find R equivalent. R equivalent is, let's put the values in meter and in watt per meter degrees of Celsius to find the overall resistance. Okay, so L1. L1 is like 2.5 centimeters, so convert it to meter over 0.1 meter squared. Okay, then you have actually what we can do here, we can take 0.1 as a common factor. Okay, let's see if we could do this. Here you have common factor, but yeah, 1 over, and those also 2 over. Okay, let's find this one. It will be 1 over RD, which is AC KB over 2L2 plus AC KD over 2L2. So you can yeah, that will be like this, right? And then after that you will take -1, so which will be like this, 2L2 over AC times KB plus KD. Okay, so it will be like this. Let me just zoom out. Here, I want to see if I have AC for all components. RBD has 1 over AC, right? Here 1 over AC, and here also 1 over RC. So I can say 1 over 0.1 meter squared is a common factor or equivalent. Then I put the other things, okay? L1 over KA, which is 0.025 meter over the conductivity of A, which is 150 watt per meter degrees of Celsius, plus you have RBD, which is 2L2, 2 times L2 has 0.075 meters over KP plus KD. Okay, so 30 plus 50, you will get 80 watt per meter Celsius, and plus you will have RC, which is L3, so 0.05 meter over 70. I'm sorry. Here B and D, we made a mistake here. I just summed between B and C. So it should be between B and D. Okay, here you have B and D. So 30 plus 70 will give you 100 here. And for C, you have 50. Okay. For C, we have 50 here. Let's put that value over meter degrees of Celsius. Okay. So I think we are okay. Let's find just the unit of R equivalent. So meter squared, and this meter squared, actually that meter will jump to the numerator. So we'll cancel all meter terms. And what remain is 1 over watt per Celsius. So it is Celsius per watt. Okay, what we get is Celsius per watt. So unit is degrees of Celsius per watt for the resistance. Okay. So 1 over 0.1 times 0.025 over 150 plus 2 over 100, and you have 2 times 0.075 plus 0.05 over 50. I think that's all. So okay, we can actually show it like this: 2 over 75. 2 over 75 degrees of Celsius per watt. Okay, our equivalent is will be equal to that value. Then so let's make this problem now. Since we know the R equivalent, we can calculate the overall heat transfer coefficient. Okay, if we remember the formula, Q for the problems that we have multiple resistance, it will be overall heat transfer coefficient multiplied by area multiplied by delta T, which is now here T4 minus T1, but the bigger value is here T1. Okay, so it will be T1 over minus T4. And what is U? And U times area, you can find U times area is equal to just 1 over R equivalent. Okay, so let's see, 1 over 2 over 75, and here you have Celsius over watt. So when you flip all these, you will get 75 over 2 watt per degrees of Celsius, which is equal to 37.5 watt per degrees of Celsius. So since you know UA, you can say now 37.5 watt per degrees of Celsius multiplied by the temperature change, so which is 370 minus 66 degrees of Celsius. You see here also Celsius will degrees will cancel each other. Then we get 11,400 watts or 11.4 kilowatts. Okay, this is the heat flow. And after that, we can use that value actually for finding all temperatures. Yes. For example, let me just show between T1 and T2. Then the remaining things maybe you can do it because it is not needed for this problem. We need only Q. But when we know Q, we can also find the other temperatures. Let me show as an example. Here you have Q coming like this. So that Q value is U A delta T, right? T1 minus T2. And you know that Q value, 11,400 watts. That equal to U times A, which is 1 over RA, okay, multiplied by T1, which is 370 minus T2. You can also plug RA value, 1 over RA. Where is RA? L 1 over ACKA. Okay, this guy here. I think this is the RA. Okay, so we will flip that to get 1 over RA. Okay, here we have 1 over RA. Then we have also temperature change here. And here it is degrees of Celsius, okay, temperature change in degrees of Celsius. So you have 1 over Celsius with Celsius, they will cancel each other. So you will have watt per meter square. Okay, watt per meter square, 1 over RA. Let me see. So you should also, 1 over RA also you have a meter square here. We forgot to put that because it is in common factor, so we forget to put that. That should be that value. Actually, you see 0.1 in besides of 150. So you have 0.1 meter square there, and that meter square will cancel the meter terms. So you have watt. Okay, as a final unit, you will have watt. So let's see how we find that value. Should be equal to 0.1 multiplied by 150 over 0.025 multiplied by known temperature, so 370 minus the unknown temperature, then shift solve, then solve for x. Here you guess, let me say 300, I'm guessing close value. Okay, so it will converge quickly when you assume the temperature value. So don't say 0, it's very close to 370. 351. So T2 found as 351 degrees of Celsius. And here you follow the same idea to find the remaining temperatures. And this is how we deal with series and parallel connections of resistant walls. I hope you understand the question. We will solve more examples in the next videos. Thank you for watching.